All right, so I think now we're ready to take on a 4x4 determinant, and we won't do it any differently. We'll go ahead and we'll start with our sign chart that will give us our cofactors. We always start with a plus in the upper left, and we alternate all the way through. So this can be done for any determinant you need. And now we pick any row or any column that we want. So from the last video, we learned if we pick a row or column with the most zeros, it's going to save some work. So just to have to pick something, I guess I'll go ahead and pick the second column here. Now, if I start in the second column, my entry to start is a -4. And remember, I'm going to be working with these signs. The negative right here means that I want to change the sign. So I'm going to have a -4, and then I'll actually have a 3x3 determinant. So if I cross out the row and the column that the -4 was in, you can see I'll have a -2, 0, -3, a 2, 4, 1, and a 3, -3, 1. So let me go ahead and get those off and rewrite. We've got a -2, 0, -3, 2, 4, 1, 3, -3, 1. Okay, now to the next entry. We have our -1 associated with that plus, so the sign will stay the same. So we'll have a plus, a -1. And the 3x3 minor, now if I cross out the row and column, the row and column that the -1 is in, we'll have the 1, 2, 0, 1, 2, 0. We'll have the 2, 4, 1, and 3, -3, 1. And then we'll move on to the 2. The 2 is associated with a negative, so it's going to be a -2. And our 3x3 that's associated with it will be a 1, 2, 0, -2, 0, -3, 3, -3, 1. And then finally we have the 0. So we'll have a plus 0, and I won't even bother writing it because we know that 0 times a real number is just going to give us 0. So right now we just have 3 different 3x3s now, in which we'll break down into 2x2s. So I'm going to start over here a little further to the left. I have a 4, and then I'll go ahead and I guess again just to be consistent here, I'll try to pick the row or column with the most zeros, and it looks like I can pick the top row on all of them. If you want to redraw your sign chart, you can. It's just going to be your 3x3. It's embedded in the 4x4, but if you want to go ahead and redraw it, you can. And so I'll go ahead now and I'll pick the -2, which stays positive. And the 2x2 for that, if I cross out the row and the column, would be the 4, 1, -3, 1. Moving on, we have the 0, which we won't worry about that. Then we'd have the -3, and the 2x2 on the -3 would be a 2, a 4, a 3, and a -3. So that whole first part there, that's just this one right here. Okay, so then I'll follow that up with a -1, and we'll go ahead and break that one apart. I think I'll go ahead and do that below. So we'll do a plus, a -1 here. And if I start with my 1, my 2x2 will be a 4, 1, -3, 1. I'll go over to a -2. Again, be careful of those signs. If I go into the -2, then my minor will be a 2, 1, 3, 1, followed by a +0, which, again, we're not going to worry about. All right, on to the last one. So we'll have a -2. We'll have the 1 out in front, The minor there would be 0, -3, -3, 1. Then we'll have a -2. The minus comes from the cofactors. And then the minor would be a -2, -3, 3, 1. And finally then plus a 0, which we know what happens there. So it looks like we actually have this whole thing here that we would need to compute. And it looks big and messy, but it's really not too bad. It's just a bunch of arithmetic. I will save a little bit of time here by just throwing the answer up on the screen. I'm hoping you feel comfortable enough to do the 2x2s on your own at this point. So just go nice and slow through it, and you should get 197 for your final answer of this one. So bottom line is you can go up to as big as you need to. It just has a corresponding sign chart. Break it down into as far as you need to get to your 2x2s, and you should be able to compute anything. All right, so now we can talk about this other technique of solving linear systems. And I do want to emphasize this: Cramer's rule only works on linear systems. So if we're trying to solve a linear system, we're going to need some x's, some y's, and if it's a 3x3, then a z. So x will end up being d sub x over d. Y will end up being d sub y over d. And then if you needed the z, z would be d sub z over d. This all only works, of course, if d is not equal to 0. Now, d is the determinant, and we'll talk about this here in a second. D sub x, d sub y, and d sub z are also determinants, but we'll have to arrange them a little differently. So let's go ahead and take a look at the example that's on the screen. Notice it is a linear system. It's a 2x2 linear system. So what we'll need to do is we're going to start with d. We want to make sure d is non-zero. D is 0. That implies something else that I'll mention shortly. But right now, we'll start with d. D is actually the determinant of matrix A. So if you guys remember from the other day, matrix A was your coefficient matrix. So 3, -2, -5, 4. And so the determinant is actually going to be the determinant of matrix A, 3, -2, -5, 4. And so if you go ahead and you compute that, you actually end up with a 2, which is non-zero, which means we can go ahead and move forward. So for us now, we're ready to compute d sub x. So d sub x is going to be a determinant. And what we're going to do is we're going to replace the x coefficients with the constants. So here are the x coefficients. We're going to replace those with the constants -4, -1. We'll leave the y's alone, which will give us another now 2x2 determinant to compute. So for d sub x, we replace the x coefficients with the constants in the equation. And when you compute this, you end up with a -18. For d sub y, we'll do the similar thing. We're going to replace the y coefficients now with the constants -4 and 1. So the x's will stay the same at 3, -5, but the y coefficients have been replaced with the constants -4, -1. And we end up with a -23 for d sub y. All right, so not quite finished yet. Our x's, remember from above, will be d sub x over d, so -18 over 2, which equals -9. Our y will be a -23 over 2. And because, again, this is a system of equations, we need to write our answer as an ordered pair. So we have the point -9, -23 over 2 as a solution to the original 2x2 linear system. Now, I mentioned before, all of this only works provided d is not 0. If you find out that d is not 0, or excuse me, is 0, if d is 0, that actually implies that matrix A is not invertible. So if d is 0, matrix A is not invertible. And if you go back to an earlier section, we talked about if A is not invertible, if the inverse matrix doesn't exist, then the solution to the original system is one of two things. It's either no solution or infinitely many solutions, in which case you could go back and use any other technique that you wanted to make that determination, and then of course express your answer in the correct way. So if that's the case, now you know how to handle that, and that wraps up this video.